In this lesson, we'll continue our conversation on area by giving the idea of a Riemann sum. And what we want to do is create what we call a definite integral. First off, what we call a Riemann sum, we partition the area under the curve. We make a bunch of rectangles like we did this time, but we don't insist that they're the same length. And we don't necessarily come up with a single set of exactly which x values to use. We just use some x value. Anyway, so what we do is if we can calculate a limit as n goes to infinity of such a sum, we call the function integrable. Integrable is more or less the idea of we can find the area under the curve. Pretty much every function we've talked about is integrable, and as long as the function is continuous, it is integrable. When a function is integrable, we're going to call this the definite integral. So compared to 4.1, we do have the same symbol here, but it does look a little bit different in that we've got numbers this time, whereas we did not have numbers before. The definite integral is what we call this value, and we're going to talk about what the value is very shortly, and I'll give you this calculation formula. We have a number called the lower limit of integration, a number called the upper limit of integration, and again this is called the integrand, and overall we call the whole thing the integral. The limits of integration you'll sometimes hear me mention. So anytime I mention those, the limits of integration are simply the numbers on the integral, and we'll talk about what they represent shortly. If we want to calculate this value, we'll use the same exact formula that showed up in the previous section. However, that formula meant area only when the function was positive. What does it mean when the function's not positive? That's what we're going to get into. Let's do an example of using this formula. It's going to be a little bit complicated, but not too bad. What we need to do is first calculate delta x. The formula is b minus a over n, which is simply 3 over n. We're stuck with that. xi is a plus I times delta x, our indexing variable. So we get negative 1 plus 3I over n. That's our xi. And so then what I want to do is, let's take a look at f of xi. Well, f of x is just x. So let me make a comment of that. Let's even write all this stuff. F of x equals x, a equals negative 1, and b equals 2. So if I plug this in for x, I just get the number right back out. That's kind of handy. Now here's our setup. We're going to do the summation I equals 1 to n of negative 1 plus 3I over n. Using what we did previously, this is the idea. I'm going to break this down into the sum I equals 1 to n of negative 1 plus 3 over n times the summation I equals 1 to n of I. If you recall, we had a formula for these. This one is just negative 1 times n, so let's just write negative n. This one's still got a 3 over n in front. And the formula for I was n times n plus 1 over 2. What we're going to do is we're going to take the summation I equals 1 to n of negative 1 plus 3I over n times my delta x, which was 3 over n. So what I get is what I had a second ago, negative n plus 3 over n times n plus 1 over 2, all times this 3 over n. And I'm going to take the limit as n goes to infinity when I'm done with this. So negative n times 3 over n is just negative 3. 3 over n times 3 over n is 9 over, I'll even write over 2n squared because there's a 2 in the denominator. And then we get n times n plus 1 is n squared plus n. So one more step, we get negative 3 plus, distributing this I get 9 halves, and distributing it to the n I get 9 over 2n. So I get, let's see, 3 is 6 over 2, so I get 3 halves plus 9 over 2n. The final step is take the limit as n goes to infinity of this. Let me actually write this as the integral. negative 1 to 2 of x dx is equal to this value, 3 halves plus 9 over 2n. Taking the limit as n goes to infinity, we know that 9 over 2n is going to go to 0, so we're just left with 3 halves. We got a number, and I will tell you, for every definite integral, your answer will be a number. If it's not, you have messed up. Let's see if we can figure out what in the world happened here. We got a number, but what does this number represent? We might be thinking of area. The problem that we just did was the integral from negative 1 to 2 of x dx. Here's what I'm going to draw you. Let's actually draw what we had here. We went from negative 1 to 2, and our answer turned out to be 3 halves. So let's analyze this a little bit. This area, which I'll color blue, geometrically has area 2. I think you guys can all see that. And this area, which I'll color in red, has area 1/2. So where did that 3 halves come from? 2 minus 1/2. That's where it comes from. So this is the value of the definite integral. This is the one that you want to keep straight in your heads. This is the main thing that I want you to get out of all the theory that I've talked to you about, is that the definite integral is the net area under the curve. That's the main thing. I showed you some summation stuff. The summation is just the theory behind it. This theorem tells you how it fits together. And in the next section, we'll talk about the fundamental theorem of calculus, which gives you a much faster way to calculate these areas if it's not easy to do based on this. If the curve lies above the axis, we call it a positive area. If the curve lies below the axis, we call it a negative area. Simply put, the definite integral gives you the sum of the positives and negatives of these areas. So let's do some examples using some geometry. We've got the integral from negative 2 to 4 of 1/2 x. That's a function with slope 1/2 and y-intercept 0. And we're looking at negative 2 to 4. If we just calculate these areas geometrically, I get 1 for this area. Base is 4, height is 2, it's 4. 1/2 base times height. This area is counted positively, and this area is counted negatively. So I get 4 minus 1 is 3. Again, I just looked at these, they're triangles, and said 1/2 base times height. Next one. X plus 2 from 0 to 3. So if I were to draw this, it's got slope 1 and passes through 2. Now this is above the x-axis the whole time. So I'm just calculating this area in its own right. And it's a trapezoid. A trapezoid, you might recall, has an area of 1/2 sum of the bases, which is 2 and 5, times the height, which would be 3. And I get 21 over 2 when I calculate that. Now you may also, if you'd like, you can calculate the area of this triangle and this rectangle and add those two together to also get the answer of 21 over 2. Next example. Square root of 9 minus x squared. Now you don't know necessarily what that shape is, but this is one that you should learn to recognize. This is a circle of radius 3. So what I'm going to do is draw the circle of radius 3. It's not a full circle, it's the top half of the circle. Try to draw this the best that I can. We're going to calculate the area, it says from negative 3 to 3. Well, that's all this area. And if we use the formula for the area of a circle and cut it in half, that'll give it to us. It's pi r squared, and r is 3. So I get 9 halves pi. With a little geometry, when possible, I can calculate the area under the curve very easily and just add or subtract as needed. The next idea is some of the properties of definite integrals. It turns out, and I think this makes sense, that if you take an integral from the same number, you don't get any area. If you think about it, there's no width of the rectangle, so of course there would be no area. If you switch the roles of a and b, it actually makes the integral negative. Okay. If you take a number c, somewhere in the middle, you can split it into two areas. The one that stops at c and the one that restarts at c. But I'll tell you a little tip. It actually doesn't matter whether c is in between them. It works for any value of c. It's just easier to notice whenever you say c is in the middle. You're just splitting it into two. Next example here, I want to find the value of 0 to 2's integral. I've got a value for 0 to 6, and I got a value from 6 to 2. First off, let me point out that the integral from 0 to 6 of f of x dx is equal to the integral from 0 to 2 of f of x dx plus the integral from 2 to 6 of f of x dx. Let's see, I want to know this one, and I know that the value from 0 to 6 is 7. Well, then I got this thing going on. Integral from 2 to 6. It's not 4. What I'm really doing is the negative, because 6 to 2 is what I have here, and I want 2 to 6. So I actually get negative 4. It looks like the integral from 0 to 2 of f of x, if I add 4 to both sides, is 11. Just some quick ideas of some of the things that you can do with these. We'll practice a few more problems. A couple other properties. It turns out, simply put, that the integral has the same properties as a definite integral as it did with an indefinite integral. You can bring constants in front, and you can split them across sums and differences. Let me just start out immediately by taking this example and splitting it into three parts. I get 3 times the integral of x squared dx minus, I got a 2 times the integral from 0 to 2 of x dx plus the integral from 0 to 2 of 7 dx. Just simply splitting them apart and bringing constants in front, now I can use these rules. Now I will say, I'm given these three integrals. This one I do not have the tools to compute in this particular lesson, so I'm just going to use the fact that it's 8/3. I'm also given that this answer is 2, but I could compute that. X, if I drew it, looks like a triangle with base 2 and height 2, so the area is 2. And then 7, if it were above the axis, would form a rectangle with width 2 and height 7, and that's why the answer turns out to be 14. Anyway, I get 8 minus 4 plus 14, I get 18 for my answer.